I just can't. I need my omega FP. I mean, I know that, and the more I teach this course, the more confident I am that you need this language if you're going to be out in the world, you know, at all, industry or academia. But maybe it's not clear. Like, none of you care about estimating the mean of a Q. I know that. But you probably will care about estimating some probability of some bad thing happening, and it's good to know it's tricky. It's, you know, and somebody can come up with a really beautiful looking answer and it's completely wrong because yeah, I should have said that. I mean, I wrote it down before. I just want to, I want to emphasize this point. A typical good algorithm will look like that. You know, a typical bad algorithm will look like this. All right. And so you go and you do your experiments, and you do them a million times, and it's like flat, and you say, I've solved the problem, but you're 50% off of reality, all right? So it really is important to know that it's a minefield simulation. It's not trivial, all right? Seeing something very flat could easily mean your algorithm sucks, all right? And that's a whole course, but just you should know it's bad. But when we get to chapter 5, it's much more apparent we're closer to the kind of applications that there's a lot of buzz about. Chapter 5 looks like machine learning all over the place, and AI. And yes, so I see some smiles. And you'll be able to try out some of these crazy things that people play around with, okay? So basically what, you know, it's really cute. I mean, chapter 5 is like an 8-page introduction to statistics, and we're just going to expand this out to the rest of the course. All right? All right. So, all right, but before I do that, any questions here?
Why is it minus I of epsilon, not just positive I of epsilon?
Well, we know that we're taking the log of a probability, so it's negative. All right? And so these i's are always defined to be positive. See, I mean, I sketched this to be positive, not negative value. Yeah, it was called the rate function, and it's always positive. It's just a notational convention. It's the same notation we used before. Okay. Okay. Anything else on this? All right. Oh man, okay. So, you know, this is the simplest example. Oh yes.
So maybe this is a question I should have asked you at the beginning.
Uh-huh.
What does asymptotic variance actually signify? Like, why are we?
Now you were just sleeping during this point when I was screaming about this being a hokey statement, right? So you know, so I don't know. Take a look at the video later, and you'll see this was a hokey. This is just an interpretation. that my estimate at time n is reality plus, in some distributional approximate sense, a standard Gaussian random variable times the standard deviation, asymptotic standard deviation divided by square root of n. So we need this to hold so there it is, you know. And so in the example, sigma squared sigma squared q is like 1/2 20 to the 4th power. And if you thought the ordinary variance was the right answer, you would get an absurdly small number. You know, the variance it's, well, approximately 20 to the 20 squared. So if you were naive enough, which is 99% of engineers, to think the variance is what you care about for simulation, almost any engineer would think that, then you get it, you know, that's nothing. You know, 400, it's like, you've barely even started. And so for the case where this was rho equals 0.95, for rho equals 0.95, 1 million is just, you're just starting, 1 million samples. You know, it's amazing. You know, for such a boring example. And consider the mean is only 20. So it's, I mean, it's 1 minus a 20, what is it? So it's 19. Yeah. So the mean is only 19. So that, you know, you'd think, God, to estimate 19, then, you know, 400 samples should be fast enough samples to estimate 19. No, but it's actually millions, you know. So, all right. So anyway, so answer your question. All right. So this is like the babyish version of what's done in chapter 5. So chapter 5 is statistics. But the word statistics is actually okay now. You used to not be able to utter that word. You know, you used to have to say learning. But that was always code for statistics. You know, machine learning means one of two things. It's optimization, and usually convex optimization, or it's statistics. You know, you know, it really, machine learning is a rebranding. I mean, of course, the applications are special, but you know, it's all that. So this is basically an introduction to AI. How's that? All right, and so I'm going to flip things around in this chapter because it starts out by just talking generally about maximum likelihood estimation, and you know, without any motivation. I'm going to flip it around and start off with hidden Markov models, and then that'll be motivation for everything else that comes. Okay, so and you know, that's a bit of a jump. All right, cool. Yeah. This is so hard. There's a lot of beautiful stuff here, but the notation sucks as usual. Yeah. Ah, boy. Okay, so you know, I'm going to be following Hayek's book really carefully. So it's section 5.3. And there's a guy at Princeton, Ramon van Handel, who's absolutely awesome. He's the most amazing teacher, and he makes lecture notes and he gives them away for free. And my favorite source for this material is on his website, and I've also sent you all his notes. It's way more advanced in this course, but if you're really going to get into this field, if you're going to get into hidden Markov models, it's the best source I know. But I'm going to stick to Bruce's notes and stick to the simplest setting possible. So what do we have? So just think abstractly first of all. So I have observations here y, just like in the Kalman filter and all that. So y here corresponds to a time series of observations. Think of the stock market, all right? And that's observed. And then you've got some hidden states in here which are not observing, and that's what, think of that is what all these jerks in Wall Street are thinking in the boardrooms. You know, when are we going to create the next recession and can cash out? but I mean, there's a, you know, it's almost a joke. I mean, you know, in the case of the stock market, there is missing information. The more information you have, the more money you make. You know, the fact that somebody, an outsider, can make any money at all is a miracle, you know, considering how much inside information there is. So, you know the stories about how they have the high frequency trading, they move their computers near the servers because the, you know, I don't know, the nanoseconds matter. You know, it's sick. It really is. I hate it. But what are the questions? You know. So one is we'd like to estimate what the other ones are thinking. We want to estimate Z. All right, that's like number one. When people talk about hidden Markov models, the assumption is that that's what you care about, right? But in the Wall Street example, what do you think the issue is in trying to estimate what the people inside those rooms are thinking? You know? There are a lot of states, there's high complexity, that's for sure. and everything about this course is about models, you know? I mean, you know, we have a model of something, you know. We have a Markov model in order to get a theory for simulation. We have, so two is that, is how to get a model which is tractable. And again, it's not like a physics problem, like an airplane, where you can talk to a physicist and an aerospace engineer, and they know that F equals ma. In the finance example, we have no idea what's going on. And we just want to look at this observed data, and based on that, make inferences about what the model is. You know, will Trump's next tweet bring down the economy? If we watch, you know, repeatedly the effect of the economy after a tweet, we might be able to cook up a Markovian model, say, of how the dynamics between the stock market and tweets and you know, politics work. You know, I mean, that's not a joke. I'm sure that's being done right now. People are constructing models, the observations of the stock market prices, the class of tweets observed by Trump, the reaction from the various presses, all of that are observations, and based on that you'd like to figure out what's going inside the system and extract as much money as you can. Yeah? All right. That used to be the thing that got students the most excited. It wasn't teaching computers to play chess. It was ripping off the public through hidden Markov models. All right, so, okay. All right, so here's the sort of the general model. Okay, so hidden Markov model, I'll write HMM, hidden Markov model. Okay, so I will sometimes accidentally say POMDP, but that's a partially observed Markov decision process. That's when you have controls. So you've got inputs to the system. So actually, for the finance example, that might be more appropriate because you have decisions to make. Am I going to buy stock or not? You know, am I going to lobby my congressperson to change some rule? I don't know. Okay, so here, anyway, here's the general model. I've got Z as a sequence. And this is supposed to represent a dependency structure. So it's an example of a Bayesian network. The fact is that, you know, I mean, I talked about this in the context of Gibbs sampling and all of that, about conditional distributions. I won't get into that. Anyway, maybe in the homework I'll give you something more general. But this defines the independent structure of the random vectors. I've got a big random vector Z and Y, which I stack up to form a giant random vector, and the dependencies are determined by this graph. I'll screw it. Nah, I wasn't planning to find a Bayesian network. I won't do it. All right, but then we've got it's Markov because Z is a Markov chain, and I'm going to. I think Bruce and I are both going to use A for the transition matrix. I believe there's a notation he uses in the book. So the probability of hopping from a state Z to a state Z prime in one step is AZZ prime. So that's the transition matrix. So I'm not using P like what was before for reasons I'll explain in a moment. Okay. So I think that's the notation that they use. And we'll take a finite state space. It doesn't matter, but we'll assume finite state space. And then we have this observation matrices. And I'm just putting these down to emphasize, we're going to assume here there's no time dependence. They could depend on time, but let's forget that. And basically those, tell you the statistics of the observations. Okay, so we're going to have a finite history that we're going to be looking at. So there's the same notation. Z is the same as writing Z1 to T, which is the same as writing this long string notation here as well.
It looks like Z1 transpose.
Yeah, I know. I'm sorry, but that's pretty standard though. Yeah, I know it looks like Z1 transpose. It's awful, isn't it? Yeah, I'll try to avoid this one. Yeah, but it's used a lot. But anyway, let's call it Z. So what do you think, given this graph structure I've written down here, what do you think this is? You know? What would your guess be? Now, a B has to show up there because B is somehow, you know, A defined this transition probabilities. And how do you think YT depends on all the Z's? That's what I wanted to ask you. What do you think B would be? I mean, given what I just said for A is like a transition. You know, the probability of my next Z is Z prime, given my previous guy is Z. So here, the Y's aren't directly coupled there. The Y's depend on each other indirectly through the Z's. And look what I'm writing here. You know, Z2.
Probability of Y1 given.
Yeah. And what's that? And that is, yes. And so we'll write B ZT to Y. All right. So there's some notation for you. All right. That's the definition of a hidden Markov model. You basically, what this is saying is this. It's really saying, remember I said that every Markov chain can be written as a dynamical system? And in fact, you prove that in the homework. You know, not only is this a dynamical system, the new state is a function of the old state and IID noise. For finite states, this Markov chain, it's linear. Remember, if you take that you proved it in the last homework. All right, this is a linear function of Z. If you set things up in the right, if you take the right representation, the right state space, it's actually linear. Well, that's always true for a time homogeneous Markov chain. This property here that YT is conditionally independent of all the other Z's given ZT means, and given the fact that we have this homogeneity here. What's that?
Why is it Markov process?
No, why is not Markov at all? Oh God, no. No, take a look. No, what?
Oh, it's not?
No, take a look. No, I said that YT is conditionally independent of all the other Z's if you're given ZT. You know? And what we're saying here is that ZT is a randomized function of ZT, you know, where B defines that randomization. All right, so it's that's really what we're looking at here. You know, that Y is just a function of a random function of that. You know, does this fit the world? It's just no. It's just that what this is. I've got these 2 degrees of freedom B and A, and it's a rich enough model to be able to fit my observations to this model. You know, so it's basically. You know, physics doesn't give you this. It's just a class of models for which a lot of theory has been developed. So you can learn A and B. You know, so goal 1. So remember I said there were these 2 goals, and one is this state estimation problem that basically I'd like to estimate this this hidden state based on my measurements. And the other is that given y, I'd like to come up, create a model, or given y and z. Now, given y and z, it's trivial. I mean, I give that to a homework problem, I wouldn't feel at all guilty. You can just write it down. But if you're only given y, that's tricky. And that's a typical situation. Like the finance example. I'm just looking at the news and the stock market. I don't know all the stuff that's going on behind the scenes. I don't have any physics to help me anything. I want to, given y, estimate these a hats and b hats and get a model. And there'll be a z. I won't know what it means. Maybe it's really strange. All right. So there's a huge science behind these two goals, and so it's because of that, it's a useful thing to know. It's a model fitting trick. All right. All right. So shall we solve goal 1? All right, so it's quite easy to solve goal 1. It's just like a deep breath again because of notation, So there's like 1a is a smoothing problem. I mean, that's funny. So the 1a is smoothing. So I'd like to know the probability of an entire string, the entire past, maybe going back 6 months. I'd like to know the whole probability of every possible string, given my observations of the last, 6 months, whatever. And 1b is just state estimation. All right, so for every possible observation, I'm going to go and watch the world evolve for 6 months. I'm going to collect in my database these observations. So to me, they're not random anymore. These are just given, right? And then based on that, I want to compute this probability. And does anybody see how you can get this from this?
Yes. If you assume Markov.
Well, no, in general. Nothing, no assumptions needed. If I know this, I know this. Marginal. That's just the marginal of that. So you get this from marginalization. Just sum out over all these guys, all the other guys. Right? This is the entire joint conditional probability. And so if you just sum out over everything but the last guy, you'll get this. Okay, so we'll review that. So that's why this turns out to be easy. That's why I'm looking at my watch and saying, yeah, we can do it. No big deal. And there's also, I don't know if we're going to do it, but there's maximum likelihood estimation. So basically, you might want, I don't want to compute this for every string. I mean, maybe there's 100 values, possible values of z1, z2, z3, and then t is 1,000. I've got 100 to the 1,000th power. That's pretty scary. And so if I wanted to try to find the most likely string, I'd be searching over this 100 to the 1000th power thing, forget it. So, but there are efficient ways to do it. So Viterbi's algorithm. Which is a workhorse in signal processing. It still is. I've never taught this subject, and I probably won't this semester either. You know, I never, it feels like it's such an outlier in the course, I never teach it. It just uses different techniques. But so this is an important topic in signal processing and communication, and just know it's in the book. I probably won't get to it. But we can do this and this. If I don't get lost in notation, we can do it in 10 minutes. I wish one of you would do it for me. So, homework, solve 1A. What would you do? Anybody remember Bayes' rule? So definitely, we definitely know the answer to this problem. It's a probability of this and this divided by the probability of this. So we just have to come up with notation so that that's not such a horrible thing to write down. So the key is the fact that if you look at the joint process, that's also Markov. And that helps a lot with the notation. And it's not that hard to see why. I mean, you know, when I look at the pair here, Y3 only cares about Z3. It's just a randomized function of Z3. And this is a randomized function of this. I mean, just take a look at this. You could put this together. I guess maybe I'm writing YT, ZT. It looks like there's a time shift I have to deal with here. But don't just plug in ZT is equal to this. You know, you can just play around. You can get the joint process satisfies the recursion just like Z does. But also just write it down. Oh. All right, so I want to show this is Markov. What I have to do is I have to look at the probability that one step in the future I'm equal to some arbitrary pair, ZT plus, these guys are arbitrary. That's in the state space and that's in the observation space. Given the past, and the semicolon just means that I'm just going to give xt a name. I'm going to call it ZT, YT. It's just a notational trick. And, you know, say t equals 4. How do I say this? So sorry. It's the I don't know why I got myself nervous. Yeah, remember I said about getting tongue-tied. I've got to go through and look at the probability. There's so much to write down. That's why it's all this stuff here I don't want to have to write all down. It's a probability that zt plus 1 equals little zt plus 1 given the past. No, that's not the right way to say it. Oh, yeah. Cool, I got it. All right, yeah, so I really have to break this down or I'll get myself messed up. So I'm looking at the probability of y given z times the probability of z, all right? And it's all conditioned. And then it's clear because y, once I know z, I just have a formula. It's just given by this monster here. And then this, I don't care, again, t plus 1 equals 4. I don't care about all this junk. I just care about z3, you know. That's the conditional independent